when you're designing for humans to be in the loop, we need to make sure that the warnings or the requests for information or for input come in plenty of time to allow the human, just like any other processor, to process that information and figure out what response they need to give and then to give that response.
Welcome to How AI Happens, a podcast where experts explain their work at the cutting edge of artificial intelligence. You'll hear from AI researchers, data scientists, and machine learning engineers as they get technical about the most exciting developments in their field and the challenges they're facing along the way. I'm your host, Rob Stevenson, and we're about to learn how AI happens. Here with me today on How AI Happens is the head of engineering over at Animal Dynamics, Ian Foster. Ian, welcome to the show. How are you today? I'm
great. Thanks, Rob. Good to be here.
So pleased to have you. It is the beginning of my day. It is the end of yours. We're a transcontinental podcast now, it would seem.
It's very exciting.
It is. And I thank you for sticking with me here and dealing with the time change. But there's so much awesome stuff to go into because of the fascinating work you're doing over there at Animal Dynamics. We will get to that. But first, let's get to know you a little bit. Ian, would you mind sharing a little bit about your background and then how you came to your current role at Animal Dynamics?
Sure. Yeah, so I'm an automotive engineer by training. I was fascinated by cars from a young age. I worked initially in motorsport and automotive on transmissions and powertrains, so very much in the sort of mechanical world. Did that for quite a long period of time and sort of generally solving the same sorts of problems all the time. You're faced with the same sort of issues that you're trying to overcome. Maybe the power's a little bit higher, maybe you want to go a little bit lighter or a little bit faster or whatever, but it's the same sort of challenges that you're being posed all the time. And I fancied doing something different and found out a bit about Animal Dynamics and what could be more different than what Animal Dynamics do. So, we're developing highly efficient autonomous systems for land, sea, and air, and sort of solving problems very much from first principles. So it's a blank sheet of paper kind of a task. There's no real preconceived or preordained direction. The limitations are much more varied than in the automotive space. And obviously drawing inspiration from the natural world to help address those problems is very much the ethos of what Animal Dynamics is all about. Not everything we do is bio-inspired. We're very pragmatic about finding the right answers for any given problem. But at the end of the day, nature has had millions of years to hone its solutions. And so there's plenty that we can learn from in that space.
It is well pointed out that there is no real playbook for the type of company, the type of tech you're building. I think everyone's probably been in meetings previously where your chief marketing officer or VP of engineering can say something like, look, I've been building ad tech products for 30 years, and this is how we've done it before, right? And that's sometimes really helpful, but not the case with the kind of technology you are developing. So we've been teasing it now for a couple of minutes, but let's talk about the actual tech you're developing. Would you mind just sharing about the mission of Animal Dynamics and how that's being carried out?
Yeah, sure. So like I said, Animal Dynamics, fundamentally, we're developing autonomous systems that solve challenging problems. There's an awful lot going on in the world today. Things are changing very quickly. There's conflict, there's climate issues, there's forced displacement of people all over the world, acute food insecurities. And there's definitely, as a result of all of those things, a need for solutions that can protect human life and to assure the delivery of essential supplies to all sorts of different environments. And a lot of those environments are quite dangerous. In many cases, the best solution to the delivery of things to people in need are going to be aerial solutions, and they're going to be autonomous solutions. So we're working on those systems, and we're working on the aspects that go around that and hand in hand with the development of that, which are the infrastructures that are going to need to support those and then to enable them. And we're also trying to understand and work through the regulatory frameworks that will keep all of us safe as we roll out those sorts of products.
Could you maybe give a real world example of where Animal Dynamics has offered a solution? What is the real world occurrence, whether it's a natural disaster or some sort of a civil unrest, something like that? What is the delivery mechanism and what is the technology actually delivering?
Yeah, sure. So you give one example yourself right there, which is a natural disaster. In the event of a flood or a landslide that is taken out the infrastructure by which people would normally be supplied with the food, the water, the medical supplies that they need. It's people who've been cut off or it's areas where the infrastructure doesn't support the delivery of those sorts of life-saving supplies. The systems that we're developing at the moment aim to fill that need, aim to get those deliveries to the people that need them, but at the same time keep human beings as much as possible out of harm's way. So that's where the autonomous aspect comes in. That's why we want something to be an autonomous system, is that you're not sending humans into a dangerous area at the same time as trying to provide for people who are already in danger.
Got it. So the why air is the best, that makes sense, because in these situations, we've all seen the news footage. This highway overpass has collapsed, right? Or this road has been flooded over. Great. So the trucks are not delivering the medicine, right? Or the hospital beds or what have you. So that explains why air is the best. And then can you speak just a little more on, it's maybe a silly question to ask on an AI podcast, but why is it better to not have pilots?
Yeah, it's a perfectly valid question. To some extent, it's easier to put a human inside this thing and let the human work out everything that needs to happen, right? It's a big challenge to make something autonomous, but the environments that we're moving into are dangerous by definition. In the event of a conflict or a natural disaster, these are uncertain conditions. They could be long distances that you're potentially traveling over, and you could be the first into that area that has changed beyond all recognition over the last 24 hours. So everything that you knew about it could now be different. As a result, humans are great. We're incredible beings and we can do amazing things. But when we're in the process of trying to protect human life on the ground, you don't want to put someone in danger if you can avoid it in order to be able to do that. So taking the pilot out of harm's way and putting them somewhere else, somewhere safe, they can operate this vehicle from somewhere that's perfectly safe. It means that you're minimizing the risk of the system that you're deploying. That goes for logistics resupply, delivering that humanitarian aid in the sort of situations that we're talking about there. But it also goes for other use cases. You could talk about aerial crop spraying, for example. That's a pretty dangerous job. The agricultural aircraft operations have a pretty poor accident record. They kill on average something like 9 pilots a year in the US alone. So, over the last sort of 5 years, they've been averaging that sort of number. And that's an area, again, where if you can take that person out of harm's way and have an autonomous vehicle in there instead, then you're protecting life.
Even in the case of those pilot flying over a farm, delivering pesticides or what have you, probably a safer scenario, flying over a giant open field than the ones you're speaking about, right? And so if it's dangerous for these pilots, it's even more so flying into the aftermath of a hurricane or perhaps even a war zone. So it makes all the sense in the world when you explain that, the opportunity to take the danger to human lives out of the equation, at least in the pilot capacity. Now, we've spoken a decent amount on the show before about some of the challenges associated with automated driving. I would love to hear you rattle off some challenges of putting that in the air. What are the unique challenges in an aerial automated vehicle?
I mean, a lot of the challenges are very similar. You need to plan a mission or a route. You need to understand where you're going. You need to monitor the environment around you and assess how that's changing and react to those changes. If you deviate from your plan, you need to manage that. You need to stay safe. All of those things are common, but there are obviously some pretty key differences. I mean, in terms of simplistically, when you're driving a car, you're on the ground, you're working in 2D, forwards, backwards, side to side. When you're talking about an air vehicle, there's a third dimension, the vertical dimension. That potentially gives you a lot more to look at and to keep track of. There's a lot more to look around you and try and spot. But at the same time, it gives you another direction that you can move in to take avoiding action from something. Obviously, depending on what the performance and the capability of your platform is, you can potentially move up or down in order to take avoiding action. It can space your obstacles out more. They can be further apart, but at the same time, they could be faster moving and coming from any direction. So the sort of perception challenge is broadened, all around the vehicle. In terms of vehicle movement, stopping isn't really an option. If on a ground vehicle, the vehicle can come to a stop if something goes wrong. With an air vehicle, you need to keep operating safely until you reach the ground in a safe manner. That's an area where some aircraft can struggle. Something like an eVTOL can potentially struggle with that. If thrust is lost, that can become a real challenge to try and manage. With the platform that we're developing at Animal Dynamics, the Stork platform, which is our aerial logistics vehicle, it's based on a parafoil wing vehicle. So it can carry quite a high payload, sort of 135 kilos. It can carry that over long distance, so up to 400 kilometers. But because it has that parafoil wing, it's capable of gliding unpowered for quite long distances. So in the event of, say, a total loss of thrust, you've still got control over the air vehicle. You can still guide it safely down to the ground and make a fairly normal landing in that instance, which some aircraft can't necessarily cope with.
It's a crucial difference between one's normal conception of a winged aircraft versus a helicopter, or what a drone basically is. A friend of mine is a helicopter mechanic, and he mentioned that if something goes wrong in an airplane, you can kind of glide it down, but your helicopter's falling right out of the sky. So with the craft you're developing there's that added element of safety. Now, is all that open airspace and that third dimension, is that an advantage just because there's more space that your craft can move in, or is it a limitation because there aren't things like stop signs and stoplights for computer vision to hone in on?
To some extent, it would appear like it's an advantage because it's a nice big open area and it's sort of not regulated in terms of what direction, it looks like it's not regulated in terms of what direction you can go in, but airspace is segregated. So there are keep out zones that you have to avoid depending on what type of aircraft that you are operating. There are segregation from altitude as well. There's altitudes you can't necessarily go above or go below, depending on exactly what sort of ground conditions you're flying over, what sort of, whether you're near an airport, whether you're near a built up area, and what your use case allows you to do, what you've had the regulatory framework sign off. So it looks like it's completely open. You can go wherever you want, but actually it's well defined as to where you can and can't fly. There's still rules to follow.
Right. And is that like a specific border that you can train the technology not to cross? It does feel like it'd be a little more challenging than say, okay, for example, this car should not drive into this wall or this fence, right?
It's definitely something that you need to add to your mission planning layer. It's definitely a set of data that you need to bring in when you're planning your route. The no-fly areas, the areas that you can't go inside, the altitudes you can't go above or below. Yeah, that all needs to be part of your mission planning, and therefore, in the event of any sort of emergency condition, you need to make sure you still don't conflict with any of those particular limitations.
So there is no as the crow flies route for this, right? And at the same time, there's also no like Google Maps or ways for you to plug in and say, okay, take this route, right? It seems like it would have to be bespoke.
Yeah, absolutely. Yeah, it is a bespoke route planning solution that you need to put in place, and at the same time as trying to put the base level of functionality in, which allows you to avoid all of the things, the no-fly zones that we've just been talking about, and takes you on the most, efficient and effective route. There may be other customer-specific aspects that they want to add in, other features. They might want something to be as fast as possible or as efficient as possible, or all the things that Google is starting to offer, that offers you. We do want to reflect some of those things, but it's starting from scratch. It's not something that's out there and available. It's something that we need to create. You
mentioned a moment ago how a car can abruptly stop if it needs to. An aerial vehicle cannot, right? It needs to come to a safe landing. Is it harder to park a car autonomously or land a plane autonomously?
They're both significant challenges. That's definitely true. So when you're parking a car, there are other road users, there are pedestrians, potentially. There are definitely things that you need to keep track of. And then there's the dynamics of the vehicle itself, the control of the vehicle, the control of the powertrain and the steering and all the other things that go into making that maneuver. You'd be a bit less worried about wind gusts, for example, when you were parking a car than you would when you're trying to land an air vehicle autonomously. So there's probably a few more disturbance inputs into that maneuver when you're landing an air vehicle. Like I said, there's a third degree of freedom that you have to worry about. So I wouldn't say it's necessarily an order of magnitude more difficult, but I think it's probably more difficult to land an air vehicle, yeah.
Ian, isn't every input technically a disturbance input?
Yes. Yeah. I mean, there's the deliberate inputs that the vehicle is putting in, but then there's the external disturbance inputs. Yeah.
Things like wind, air pressure.
Yes.
Other aerial bodies.
Yes. All the things that the perception system is perceiving around the vehicle that it wants you to take account of, and it needs the control system to be able to take account of.
I'm personally constantly disturbed by inputs, so I understand that compulsion on the part of these drones. But could you speak a little more about the automated landing? Are these vehicles detecting runways, or how are they managing to land themselves?
So the vehicle that we're developing, the Stork vehicle that we're developing, is intended to not need a huge amount of ground-based infrastructure. So because of the sorts of use cases that we've talked about, the sort of humanitarian aid delivery and those sorts of operations, these aren't necessarily areas where you're going to have a pre-prepared runway to go and land on. It needs to be able to deliver or to land in as many places as possible. So we're trying to land somewhere that's relatively unprepared as much as possible. In terms of making that landing, the end goal is to have a system where you can point it where you want to go, click somewhere on a map, and the system will fly there and get to that position and assess whether or not that's somewhere it can land. And if it can, then it'll go ahead and land there, and it'll pick out all of the features that it needs to in order to make sure it lands safely and brings itself to a stop. That's a process that we need to build up to. That's something that we need to start off with a proportion of that capability and build towards it. So the initial rollout of that capability is something short of that, where we direct it to a landing point and we get to that landing point, and maybe it takes an image of that. Maybe it sends that back to base and says, is this okay? It looks like it's okay to me. Do you agree that this is still an okay place for me to land? And then we take that learning and we build up from there. And as we improve our perception systems recognition of features on the ground, whether that's through a LiDAR system that's picking out particular features, or whether it's through optical sensors, cameras using image detection and recognition of various different objects on the ground. We build up that capability, and we're using those different sensor inputs to assess whether or not that landing site is still appropriate and whether or not that's somewhere that we can put down.
So as far as I know, there's no Google CAPTCHA for click on all the tiles that have safe landing zones. So where is the data coming from, and how are you going to train the technology to notice a safe landing zone?
Data for autonomous aircraft is definitely a big challenge, as you might imagine. So for landing sites, there are sets of satellite data publicly available that covers the whole planet. Some of those data sets are already segmented to divide the data sets up into different categories of land use. And obviously we can create and have created, machine learning algorithms that will take those data sets and segment them for ourselves. That allows us to do route planning and to select landing sites from satellite data. You obviously need to overlay other sets of data and fuse those together in order to get the full picture. So ground elevation data, for example, to assess gradients, land use case data, no-fly zones and things like that, which will allow us to plan the route, but also to then select the landing site. But it's an even bigger challenge than that, because ultimately the real world is changing. There might be data sets out there, but at a very basic level, the northern hemisphere in winter looks very different to how it looks in summer. So that sort of satellite data, the algorithms that we're training on that data need to understand how those landscapes change as the seasons change. And then again, to go back to the use cases we've talked about in the event of a natural disaster, what you're looking for in terms of a landing site might not be there anymore because there's been a flood or there's been a landslide or something similar. The ground picture can change wildly. So the mission planning data that you do based on readily available pre-prepared data gets you so far. It gets you a planned mission, but you still have to assess the ground that you're flying over as you're progressing, as the mission unfolds. We can use test vehicles for things for in-flight. We can fit a combination of sensor types to test vehicles, INS, radar, LiDAR, cameras, and gather that data for ourselves. And there's also obviously simulation environments. We can use simulation to challenge our systems against simulated events to assess its behavior and its performance. For those simulations, you'll need good models of the sensors that you're using, and good models of the rest of the system. And then you can build up a full system model and check its response. That could be a simulation of just the perception system in isolation, or it could be a simulation of end-to-end, the perception system perceiving something, the control system then, initiating a response, and then the vehicle dynamically responding to avoid something or during a landing run. You can assess the vehicle's behavior end-to-end. Fundamentally, to touch on a point that I mentioned before, fundamentally it's about a staged rollout of capability. And we're doing that in controlled environments. So we're not aiming to just jump straight to full autonomy from day one. We need to take a staged approach to that, building the capability, building the knowledge that we have, and assuring that we steadily expand our operating envelope. So we start with a proportion of the capability, we operate safely within a controlled environment, and we gather data the whole time that we're doing that. And then as we prove out more aspects of the system performance, we can grow that envelope and expand the operating environment that we're able to work in, and then prove out the next level. That means that we can actually get these systems out there and working in the real world in controlled cases, controlled use cases, but actually start to make a difference to people's lives and actually start to make a difference out there with our products before the full capability is available. We can still deliver something that's going to make a difference to people, even if we've only got a proportion of that capability. But the key to that stage rollout is actually keeping humans in that loop at the right level as we progress.
I'm glad you mentioned human in the loop because I wanted to make sure we spoke about that. So where does the human in the loop involvement make the most sense? And then how do you decide where to implement it?
As we're developing the Stork aerial vehicle, this is all part of the systems engineering process. The various different actors who interact with the air vehicle are all part of the overall system. So they all provide inputs, they take outputs, they give and receive information, just like any other part of the system. So the process of designing the system looks at the flow of data, the flow of that information around the system. And you need to understand what the limitations of each part are. Where is it best to get the information from? Can we rely on that sensor at this moment? Or can we rely on that actor at this moment? Where is our redundancy? What's the latency of the signal that we're receiving? And so while you're developing the system and understanding the system like that, you can choose where you'll need human input because we don't quite trust yet the signal that we're getting from that sensor, or where do you need a human at least to oversee the input that's coming from that sensor and provide a check on the information that's coming from that sensor or from that system. So that's all modeled during the design process, and it's revisited as the system is changed and upgraded, and you make sure you do the right safety analysis to make sure that we're safe to operate. So the design process tells us where we'll need human oversight for a decision. And at the earlier stages of development, those instances are going to be more common. They're going to appear in more areas because you're still in the process of building confidence with the different parts of the system that are providing the information and making the decisions. The modeling also tells us whether there's going to be enough time for that human to actually make that intervention. And that can be a risk. For example, with the early implementations of autonomous driving, that's something that we do see in those sorts of situations. So the system's working fine, the vehicle has control, but at the point where the car decides it doesn't know what to do and hands back control, the human's supposed to then take over. But if it was something really straightforward, the car would probably know how to handle it, right? The car would probably already be able to deal with it. So there's a good chance that when it needs to hand back to the human, it's actually something quite complex that it doesn't know how to handle. And that might require 100% of the driver's concentration. So the driver goes from 5% to 100% in a split second, and that's a pretty tricky shift to make. So when you're designing for humans to be in the loop, we need to make sure that the warnings or the requests for information or for input come in plenty of time to allow the human, just like any other processor, the human to process that information and figure out what response they need to give and then to give that response.
If you have a human in the loop process whereby the human goes from sitting on the bench cold to running on the field sprinting and making a split second intervention, then you don't really have autonomy because they would have needed to be paying 100% attention that whole time to successfully make the intervention, correct? So that's interesting. Yeah, as you said, an early problem with at what point do you give control back to the human? You sort of set them up to fail a little bit. If it's like, okay, you have to be this involved the entire time to make this judgment. Is the goal then for the human to be continually less in the loop, I guess, as you've talked about this phase rolling out of the autonomy of your tech? Obviously, over time, less and less human involvement necessary, correct?
Yeah, that's definitely the aim. Ultimately, the desire is that these systems basically look after themselves and that humans are only involved in telling the thing where to go, and then the rest of it is delivered autonomously. But like I say, the important thing for us is to get out there and start making a difference to people. And so we need to find a pragmatic and safe way of doing that. So to begin with, keeping humans in that loop and having humans in the loop probably quite a lot to begin with is inevitably the way of doing it. But yes, the aim is ultimately to ramp that down and ramp up the autonomy of the vehicle and take more decisions and do more assessment of the signals automatically on the vehicle and take the human decisions out.
Could you give some examples of where precisely in the loop the humans are at this moment?
We're still in the development phase at the moment with the vehicle, so humans are quite heavily in the loop right now. we're still looking to double check effectively the decisions that the vehicle is making. So the vehicle is typically making recommendations at the moment and then getting some sign off from the human to say, yes, you've made the right decision, go ahead. So we're trying to build in the ability of the system to make an assessment from the start, but the human will have oversight essentially and confirm that that's the right way to go for quite a few decisions. There'll be a whole bunch of flight control stuff that the vehicle looks after for itself, but key things like coming into land and making a landing site assessment and stuff like that, that's going to be checked to begin with, probably just to make sure, because that's where you're entering into areas of highest risk.
Not dissimilar from commercial aircraft, by the way, right? I understand that the humans are really involved in takeoff and landing, and then that the plane kind of flies itself. Once you reach cruising altitude, it's doing a lot on its own. Is that accurate?
That's how I understand it. Yeah. I mean, like I say, in terms of aerospace, my experience is largely around animal dynamics, but that's what I understand too. It's a keep the humans in the bits that are of highest risk and then allow the system to take over when appropriate.
So before I let you go, Ian, I want you to kind of indulge this technology a little bit to its utopian sci-fi climax. What do you think is the opportunity, the long-term opportunity for this sort of automated disaster response with regard to animal dynamics, but then in terms of aerial autonomy writ large?
In terms of the future, it's probably a question of scale. So it's a question of the amount of situations and areas that this technology can be deployed in, and the reliability of it delivering in those areas with progressively less human involvement. So it's scaling up from a single vehicle operating on its own to multiple vehicles operating in a coordinated fashion. They're working together and swarming effectively, working cooperatively to concentrate their effort in the areas that are best needed. So there are aspects of bioinspiration that can be taken in those areas too, in terms of the control of the vehicles, in terms of the control of a fleet of vehicles. We can look at insect swarming and the way that they combine in order to maximize their impact and things like that. So it's probably controlling multiple vehicles, fleets of vehicles, swarms of vehicles that is going to be kind of the direction that this is going in. Once we've got the unit behavior, once we have one of these systems working correctly, you can then connect multiples of them. And then the impact of them can be multiplied. The problems that they can solve can be multiplied in many different areas.
Got it. Well, Ian, this has been a fantastic discussion. I'm fascinated by the tech you're developing, and the mission is really honorable as well. Not merely trying to scrape some millions away from United Airlines, you're also trying to deliver help to people who really need it. So congratulations on what you've accomplished so far. And I'm just so pleased that you agreed to meet with me. This has been a fantastic conversation. So thank you for being here today, Ian.
No problem. Thank you very much.
How AI Happens is brought to you by Sama. Sama provides accurate data for ambitious AI. Specializing in image, video, and sensor data annotation and validation for machine learning algorithms in industries such as transportation, retail, e-commerce, media, medtech, robotics, and agriculture. For more information, head to sama.com.